Alright, here's a video on indefinite integrals and antiderivatives. So, quick recap. What have we used derivatives for? Because we're about to do the opposite, and it's kind of cool what they stand for. So it's good to think about where we are now. What have we used derivatives for? The first thing we used derivatives for was to find instantaneous slope, right? And then we used it to find tangent lines. And then we used it to find velocity and acceleration problems, right? And then we did related rates. We used derivatives for all these things. Then we used it for critical numbers and inflection points and increasing and decreasing. We could figure out when our graph was going up, when our graph was going down. We used it to find max and mins, or extrema. We used it to find, or to sketch curves, right? Concavity. So there's a ton of stuff we used derivatives for. So now we're going to learn how to do these kind of backwards. So what if we know that the derivative is 3x squared? What could regular f of x be? And if you think about it, think about your normal derivative rule. Like if I had, here's a different function, 6x to the fifth. If I had this, my old rule for derivatives was to multiply in front and then knock the exponent down one, right? So think about this. Which equation could be one that multiplied in front and then knocked the exponent down one? Most of you are probably thinking it's probably x to the third. You can check if you're right. Take the derivative of this guy. 3x squared. Hey, I win. But it's not the only correct answer, because that weird fact that when you take the derivative of a constant, it goes away, makes there a whole lot of answers, right? In fact, I could do this all day. I take the derivative of that, I still get 3x squared. And there's a reason for that. If you looked at the picture, remember how derivatives find instantaneous slope? If I looked at any of these graphs, let's not look at the 100 one, but if I looked at x cubed, the graph would look like this, right? If I looked at x cubed plus 6, it's the exact same graph, just shifted up 6, right? So if I'm talking slope, the slope at this place, if I looked at its slope, is the exact same slope at that place. And if I looked at x as 1, the slope at this place is the exact same slope at that place. So shifting a graph up or down doesn't change your slope, which is why adding or subtracting any number at the back doesn't change your derivative. So instead of trying to write 1 million different answers for this, or an infinite amount of answers, we kind of found a shortcut, and we said our answer that has this derivative must be x cubed plus some constant. And we use a c, and that's why these are called indefinite, because it's kind of unknown. There's a ton of different answers, and it's not quite definite what the real equation was to start with. So we're going to get a little notation here. Let's do notation. These are actually, you're just learning the rule for the opposite of the power rule today. If the original function is f of x, then the antiderivative, so to go back a step, we already know if you have f prime and you go back a step, you go to f of x. But if you go back a step from f of x, it's called an antiderivative. antiderivative would be, and you go capital F of x. So if you go down a step on the ladder, you use primes. If you go back a step on the ladder, you use capital X. So if I took the derivative with respect to x of capital F of x, it's going to equal regular f of x. The derivative of this guy equals that guy, or the antiderivative of this guy equals capital F of x. So that's just a little notation for you. A little more notation while we're in the wheelhouse here. Here is what, you know how d over dx tells you to take a derivative? What symbol tells you to do an integral or an antiderivative? Kind of similar. This symbol, this is called the integral symbol. It looks like an S that's been stretched out vertically. Kind of looks like a musical sort of thing too. So think of these as like parentheses. Like this is the beginning of your parentheses, so it's the beginning of your problem. The dx at the back is the end parenthesis, and everything it contains inside is the thing you're going to take the antiderivative of. This basically tells you you're going to take the antiderivative with respect to x. Similar to how I had to know I'm taking the derivative with respect to x. It makes sure your letters match, you know. And what's it going to equal? Capital F of x plus c. So how would I pronounce this? Because I want you guys to sound like you know what you're talking about. You would say the integral of f of x with respect to x. That's what you would say for this side. And what does it equal? It equals the antiderivative of x plus c, plus a constant. So that's some terminology. Integral symbol. The whole thing is you say integrate f of x with respect to x, and that's an antiderivative. It's basically when you use the opposite of our derivative rules. Okay, so moving on. Basically, we're doing the opposite. These things are inverses of each other. Which means if you take the integral of a derivative, since they're opposites, you know that's a derivative, it has the prime, it equals your original function, plus c. You cannot forget the plus c. The other way around is, what if I took the derivative of an integral? So here I would get a capital F of x plus c, and then I take its derivative. Well, the c would go back away, and you get the original function again. So this just says it actually does work like an inverse. It's just like squaring is the inverse of square rooting, and multiplying is the opposite of dividing, inverses of each other. Well, integrals are the inverse of derivatives, and derivatives are the inverse of integrals. Fun thing. The only thing you have to remember is that plus c, and I know you'll forget it, but you have to try to remember it. All right, so let's look at some old rules. I'll set up a table real quick. All right, so these are our integration rules. There aren't as many because there's no product rule and there's no power rule, which is kind of cool. But take a minute, pause this, and set up your own table. All right, so our old rules, when I say that, is our derivative rules. And our new rules are going to be our integral. And you'll start to notice is they do the opposite of each other. Okay, so if we had an old rule that said the derivative of a constant, right? What did you always get as an answer when you took the derivative of any constant? You got 0. Well, guess what you get when you take the integral of 0? You get a constant. It's the reverse. If the derivative of a constant is 0, then the integral of 0 must be a constant. Similarly, what do we get if we took the derivative of 5x? Right? Easy, right? 5. Well, guess what you get if you take the integral of 5 with respect to x? you get 5x. But wait, there's more, plus c. Because remember that whole shifting up and down doesn't change the slope? You never know. If I took the derivative of that, I would get 5. If I took the derivative of that, I get 5. So, and here's the really important one. Remember our rule. The rule we use more than any other rule is called the power rule. And you take the old exponent in front times x to the n minus 1. That's our rule making derivatives. Our new rule, and the most important rule you're going to know for antiderivatives, is if you're ever asked to take the integral of x to the n, you're going to do the opposite stuff. So think about the order I did it in, because even the order's opposite. I took the old power and put it in front first, and then I subtracted 1 from the exponent. So we're going to do this in total reverse. I'm going to add 1 to the exponent, so it's going to be x to the n plus 1. That makes sense. It was minus 1, now it's plus 1. And instead of multiplying, we're going to divide by the new exponent. So the order changed too. Remember the first thing you did in this problem was multiply and then you take the power down 1? This is backwards. You take the power up 1 and then you divide by the new power. Okay, so this rule right here is what we're going to use over and over and over and over again until you get good at it. Let's do a couple examples. Okay, and this is what your homework is like. You're just going to crank out examples till you're good at these. And you are not going to forget the plus c's. Right? Right. Okay, usually we do this. Sometimes people don't put the parentheses and we still know what you're doing because that acts like a start and that acts like an end. Okay, so let's try our new rule. Okay, so I'm going to take the old power up 1 and I'm going to divide by my new power, 3. And I'm going to take my, there's still a plus between them. I'm going to take my old power up 1. Now if you don't see it, there's a 1 there. I'm going to raise it up to a 2 and divide by the new exponent. And I'm going to put a plus c because I'm not a rookie. And then simplify your answer. The 3's cancel and the 2's cancel. Now, here's a cool thing. You are your own answer key. If I asked you if I did it right, you could just take the derivative of this, and the derivative of this, and the derivative of this, and it should equal what's in here. So that would be 3x squared plus 2x plus nothing. 3x squared plus 2x. Boom! Winner, winner, chicken dinner. Right? Let's do a couple more. Okay, this is a big one, but it's still the same thought process. You take the old number, even with the number in front of it, and you raise the power up 1, and then you divide by the new exponent. I take the old number, I raise the power up 1, divide by the new exponent. Take the old number, 4x, raise the power up 1, divide by the new number. Take the old number, 6x, raise the power up 1, divide by the new exponent. And last but not least, the 3, you take the old power and move it up 1. Most people don't see this, but it's 3x. Just think backwards. What would have a derivative of 3? Oh, 3x. Now don't forget your plus c, and then we simplify a little bit. Some of them get a little nicer. Like this becomes x to the 4th over 2, or 1/2, because you got 2 over 4. Right? Here it doesn't simplify, so I didn't want you to think they always turned out nice. Oops, put a plus there. So negative 3x squared, 6 over 2 is 3. 3x plus c. Boom. That is the integral of that one. So it's the antiderivative. All right, just a little bit of time left, so I'm going to go into hyper mode here. Sometimes you have to rewrite it, just like when we did derivatives. Rewrite it, and then you can make the power go up by 1. Remember, up by 1 is a negative 2. Divide by the new exponent, plus c. Awesome. You could rewrite that again and say, you know, that would be the prettier way to write it. Drop that back down. Okay. Down here, I could rewrite this as x to the 3/5. And then I make the power go up by 1. What's 3/5 more? Or 1 more? It's 5/5 more. So you're going to go 8/5. And how do you divide by 8/5? You put 5/8. You do the reciprocal. Awesome. And one more thing, split this up just like in the past.